October 19, 1944, 23,000 feet above Kassel. Lieutenant Colonel Francis Gabreski's Thunderbolt shuddered as German flak burst around him. Below, a formation of B-17 seconds crawled toward their target, and above them, diving fast, came 6 Focke-Wulf 190s. Gabreski pushed his throttle forward to military power, the R-2800 engine roaring behind its cowling. The Focke-Wulfs were closing on the bombers at 400 miles per hour. He needed more speed, more climb, more everything. His hand moved to a small red lever on the throttle quadrant, protected by a wire guard. The placard beside it read, "War Emergency Power." He flipped the guard open and pulled. Instantly, a fine mist of water and methanol sprayed into the engine's supercharger. The intake temperature dropped 60 degrees in seconds. Manifold pressure surged from 52 inches of mercury to 70. The Pratt & Whitney engine, already producing 2,000 horsepower, suddenly screamed out 2,500. The Thunderbolt leaped forward like it had been kicked. Gabreski closed the distance in seconds, lined up on the lead Focke-Wulf, and fired. The German fighter disintegrated. The other 5 scattered, abandoning their attack run. They'd never seen a P-47 accelerate like that. Neither had Gabreski, until 3 months earlier, when Republic Aviation had quietly installed a 15-gallon tank in his fighter's belly. That tank contained a 50-50 mixture of water and methanol, and it had just transformed his Thunderbolt from a formidable fighter into something the Luftwaffe had no answer for. The Germans knew about water injection. They'd used it on their own fighters for over a year. What they couldn't understand was why the American system worked so much better, lasted so much longer, and seemed to be installed on every single Thunderbolt coming off the production line by late 1944. The answer wasn't a secret weapon. It was American. Industrial philosophy made manifest. A simple, reliable system that could be mass-produced and installed on thousands of aircraft without compromising structural integrity or maintainability. But getting there required solving problems that had killed test pilots and destroyed engines. The story of water injection in the P-47 is a story of thermodynamics weaponized, of marginal gains that produced overwhelming advantages, and of German engineers watching helplessly as American fighters exceeded performance parameters they knew were theoretically impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The concept of water injection wasn't new in 1944. Engineers had understood the basic principle since the 1920s. Spray water into an engine's intake, and you cool the incoming air charge. Cooler air is denser. Denser air contains more oxygen. More oxygen allows more fuel to be burned. More fuel means more power. The chemistry was elegant, but the engineering was a nightmare. Water doesn't compress. Introduce liquid water into a cylinder where a piston is trying to compress an air-fuel mixture, and you get hydraulic lock. The piston can't move. Connecting rods bend, crankshafts snap, engines explode. The key was atomization. The water had to be injected as an ultrafine mist that would flash vaporize in the hot intake manifold before reaching the cylinders. That vaporization was critical because when water turns to steam, it absorbs enormous amounts of heat. 1 gallon of water vaporizing at atmospheric pressure absorbs over 8,000 BTUs of thermal energy. In the supercharged environment of a P-47's intake manifold, that heat absorption dropped intake temperatures from 250 degrees Fahrenheit down to 190. That temperature drop was worth its weight in ammunition. Internal combustion engines are limited by detonation, the phenomenon where fuel-air mixture explodes chaotically instead of burning in a controlled flame front. Detonation destroys pistons, punches holes through cylinder heads, and can grenade an engine in seconds. Higher manifold pressure means more power, but it also increases the risk of detonation because you're compressing more fuel and air into the cylinder, raising temperatures and pressures. Water injection attacked detonation from multiple angles. First, it cooled the intake charge, reducing the likelihood of pre-ignition. Second, when water vaporized inside the cylinder during combustion, it absorbed heat that would otherwise contribute to detonation. Third, the water vapor physically displaced some of the oxygen in the cylinder, creating a buffer that slowed the flame front and prevented the supersonic pressure waves that characterize detonation. Methanol, typically mixed 50-50 with water, added its own benefits. Methanol is alcohol. It burns. Unlike water, which simply absorbed heat, methanol contributed additional fuel to the combustion process. A 50-50 water-methanol mixture gave you cooling from the water and extra energy from the methanol. But methanol had another critical property. It had a lower freezing point than water. Pure water freezes at 32 degrees Fahrenheit. At 25,000 feet, outside temperatures routinely dropped to -40. A pure water injection system would freeze solid, clogging lines and destroying pumps. Methanol depressed the freezing point of the mixture to around -50 degrees, keeping the system liquid at operational altitudes. Republic Aviation's engineers hadn't invented any of this. General Motors' research division had experimented with water injection on ground engines in the 1930s. The Luftwaffe had installed methanol water systems on some DB605 engines by 1943. What Republic did was take the concept and engineer it for mass production with reliability that could survive combat conditions. The challenge was integration. You couldn't just bolt a tank and some spray nozzles onto an existing P-47 and call it finished. Every system on the aircraft was interconnected. Add 15 gallons of water methanol weighing about 95 pounds, and you shifted the center of gravity. That required recalculating weight and balance. The tank itself had to fit somewhere in the already packed fuselage without interfering with control cables, hydraulic lines, fuel lines, or the complex turbocharger ducting that defined the Thunderbolt's architecture. Republic's solution was elegant in its simplicity. They placed a vertical cylindrical tank in the fuselage behind the pilot, just forward of the radio equipment bay. It was accessible through a small hatch for servicing, and it didn't require major structural modifications. Gravity fed the fluid from the tank to an engine-driven pump that pressurized the system to 40 pounds per square inch. From there, lines ran forward to spray nozzles positioned in the supercharger intake ducting, just before the air entered the intake manifold. The nozzles were critical. They had to atomize the fluid into droplets small enough to vaporize completely before reaching the engine, but they also had to flow enough volume to provide adequate cooling. Too little flow, and the system wouldn't prevent detonation. Too much flow, and you'd get liquid water in the cylinders, which meant catastrophic engine failure. Republic tested dozens of nozzle configurations at their Farmingdale facility through the winter of 1943 and 44. They ran R2800 engines on dynamometers, injecting various flow rates while measuring manifold pressure, cylinder head temperatures, and exhaust gas temperatures. They deliberately pushed engines past their limits to map the boundary between maximum power and destruction. The target was clear: 70 inches of mercury manifold, pressure. At that pressure, the R2800 would produce approximately 2,500 horsepower, a 25% increase over its rated military power output of 2,000 horsepower. But 70 inches was also the threshold where detonation became almost inevitable without some form of charge cooling. Water injection had to prevent detonation at 70 inches for at least 5 minutes, giving pilots enough time to execute combat maneuvers, make an escape, or press an attack. 5 minutes doesn't sound like much, but in aerial combat, 5 minutes is an eternity. Most engagements lasted less than 30 seconds, from initial contact to one aircraft being shot down or breaking off. 5 minutes of war emergency power gave a pilot multiple engagement cycles. The testing wasn't just about preventing detonation. Engineers had to ensure that the methanol in the mixture wouldn't damage engine components. Methanol is a solvent. It attacks certain types of rubber and can corrode aluminum if not properly inhibited. Republic's engineers tested O-rings, gaskets, and seals for methanol compatibility, replacing components that showed degradation with methanol-resistant materials. They added corrosion inhibitors to the water-methanol mixture and specified strict mixing ratios that had to be maintained during field operations. By March 1944, the system was ready. Republic designated it the ADI system, standing for Anti-Detonation Injection, though pilots would universally call it War Emergency Power, or simply WEP. The first production P-47 seconds with ADI systems rolled off the Farmingdale line in April 1944, designated P-47D-25RE. The modification added approximately 120 pounds to the aircraft's total weight, including the tank, fluid, pump, lines, and nozzles. That was acceptable. The performance gain was anything but marginal. Test pilot Mike Quinlan took the first ADI-equipped P-47D-25 up on April 7, 1944. Farmingdale's sky was clear, temperature 45 degrees at sea level. Quinlan climbed to 15,000 feet, leveled off, and stabilized at military power. Manifold pressure, 52 inches. Engine temperature, normal. Airspeed, 320 miles per hour. Then he activated the ADI system. The change was immediate and visceral. The engine note deepened as manifold pressure climbed to 70 inches. Quinlan felt himself pressed back into the seat as the Thunderbolt accelerated. He glanced at the airspeed indicator, 340 miles per hour, 360, 380. At 15,000 feet, in level flight, the P-47 was now indicating speeds it previously could only achieve in a shallow dive. Quinlan let the speed stabilize at 395 miles per hour, then pulled back into a climb. Standard P-47D-22 without ADI could manage around 2,700 feet per minute climb rate at that altitude and weight. With ADI active, Quinlan's rate of climb indicator showed 3,400 feet per minute. He climbed through 20,000 feet, still pulling 2,800 feet per minute. At 25,000 feet, where non-ADI Thunderbolts would be struggling to maintain 2,000 feet per minute, Quinlan was still climbing at 2,400 feet per minute. He shut down the ADI system at 30,000 feet, having used it for approximately 4 minutes. The engine temperatures had risen, but remained within acceptable limits. No detonation, no unusual vibrations. The system worked flawlessly. Republic's production engineers moved fast. By May 1944, all new P-47Ds coming off both the Farmingdale and Evansville production lines included ADI systems as standard equipment. Retrofitting older aircraft in the field proved more complex, but Republic developed field modification kits that could be installed by squadron maintenance crews in about 40 hours. By June 1944, weeks before D-Day, roughly 30% of 8th Air Force Thunderbolts in England had been upgraded. By September, that figure exceeded 80%. The transformation in combat capability was immediate and profound. Pilots who'd been flying P-47 seconds for over a year suddenly found themselves in aircraft that could outclimb, out-accelerate, and outrun anything they'd previously experienced. More importantly, they could do things that made German pilots question their own aircraft's specifications. Major Gerald Johnson of the 56th Fighter Group first used ADI in combat on June 23, 1944, during a bomber escort mission to Berlin. His flight of 4 Thunderbolts was cruising at 28,000 feet, when German fighters appeared below them at 22,000 feet, climbing to intercept the bomber stream. Johnson radioed his flight and rolled into a dive, standard boom and zoom tactics. But as he approached the German fighters, several Focke-Wulf 190Ds broke formation and dove away, trying to escape. Normally, Johnson would have had to choose: follow them down and give up his altitude advantage, or let them go. Instead, he activated ADI and pushed the throttle past the military power detent into the war emergency power range. The Thunderbolt surged forward. Johnson stayed in his dive, but instead of building up speed gradually, the ADI-boosted engine pushed him past 450 miles per hour in seconds. He caught the diving Focke-Wulfs, fired a long burst into one, and watched it tumble out of control. Then, instead of continuing down where he'd be vulnerable, Johnson pulled back into a steep zoom climb. Normally, a P-47 pulling out of a 450-mile-per-hour dive would climb well initially but then bleed energy rapidly, eventually settling into a lower climb rate. With ADI still active, Johnson's Thunderbolt climbed like it was defying physics. He regained 25,000 feet in less than 90 seconds, rejoining his flight with barely any energy loss. The other German fighters had scattered. Johnson's after-action report was clinical, but his verbal description to squadron mates was enthusiastic. He told them the ADI system made the P-47 feel like a completely different airplane, one that could dictate terms of engagement at will. Word spread fast. Pilots began experimenting with ADI in various tactical scenarios. Some used it for emergency escapes when they found themselves outnumbered or in disadvantageous positions. Others used it offensively, activating ADI during initial attack runs to close distance faster than targets expected. A few creative pilots even used it defensively in turning fights. The P-47 couldn't outturn a Focke-Wulf or Messerschmitt in sustained horizontal turns, but with ADI active, it could convert vertical energy into tight climbing spirals that left German fighters struggling to follow. The statistics started coming in by late summer 1944. Fighter groups equipped with ADI-equipped P-47 seconds reported kill ratios averaging 4.2 to 1 against Luftwaffe fighters, up from approximately 3.1 to 1 for non-ADI-equipped units operating in similar conditions. Part of that improvement came from pilot experience and overall Allied numerical superiority, but pilots consistently reported that ADI gave them decisive advantages in specific engagement types: high-speed chases, zoom climbs after diving attacks, and emergency escapes from bad tactical positions. The Luftwaffe noticed immediately. Interrogation reports from captured German pilots in July and August 1944 repeatedly mentioned Thunderbolts that accelerated impossibly or climbed faster than any P-47 should. German intelligence officers initially dismissed these reports as exaggeration or pilot error. The P-47's performance envelope was well documented through captured aircraft and technical intelligence. The reported performance exceeded those parameters by margins that suggested either instrument error on the German side or wishful thinking. But the reports kept coming. By September 1944, enough captured Thunderbolt wreckage had been examined that Luftwaffe technical intelligence confirmed the existence of an additional tank system in newer P-47 variants. Chemical analysis of residue in recovered tanks revealed water and methanol, and German engineers quickly understood what the Americans had done. The conclusion was sobering. The Luftwaffe's own MW-50 methanol water injection system, used on some DB605 and BMW 801 engines, provided similar power increases but had critical limitations. German systems were typically limited to 1 to 3 minutes of operation due to smaller tank capacities and concerns about engine reliability. The American system, from examination of recovered aircraft and pilot interrogations, appeared to function reliably for 5 to 10 minutes. Moreover, the American system seemed to be installed on virtually every new P-47 coming off production lines. The Luftwaffe's MW-50 systems, by contrast, were installed on only select high-altitude variants and specialized fighters due to production bottlenecks and material shortages. Germany's synthetic fuel industry was struggling by late 1944, and methanol production competed with other critical chemical needs. Methanol could be used for injection systems, or it could be used in synthetic rubber production, or aviation fuel additives, or dozens of other applications. The Reich simply didn't have enough to go around. Part 2 begins. America's approach was fundamentally different. Republic Aviation wasn't rationing components. They were installing ADI systems on every Thunderbolt as standard equipment. The water-methanol mixture itself was cheap and easy to produce. Water was free. Methanol could be synthesized from coal or natural gas, resources America had in abundance. Ground crews could fill ADI tanks as routinely as they filled fuel tanks, oil reservoirs, and ammunition bays. The system wasn't a special modification for elite units. It was baseline capability for every P-47 pilot in theatre. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Major Gunther Rahl, one of the Luftwaffe's highest-scoring aces with over 270 victories, encountered ADI-equipped Thunderbolts in September 1944 during combat operations over Western Germany. Rahl was flying a Messerschmitt Bf 109 G14, itself equipped with the MW50 system. He spotted a formation of P-47 seconds escorting bombers at 26,000 feet and positioned his flight above them at 30,000 feet, the classic altitude advantage. Rahl initiated his attack, diving on the trailing Thunderbolt with speed and altitude superiority. Standard doctrine suggested the American would either turn to defend, sacrificing speed, or dive away, giving Rahl time to follow and fire. The P-47 did neither. It accelerated in level flight, then pulled into a steep climbing turn. Rahl followed, activating his own MW50 system. His engine roared, manifold pressure climbing, and the Bf 109 stayed with the Thunderbolt initially. But after approximately 90 seconds, Rahl's MW50 tank ran dry. The system automatically shut down. Power dropped back to normal military settings. The Thunderbolt kept climbing, its ADI system still active, still pouring water and methanol into the supercharger intake. Rahl watched the American aircraft pull away vertically, gaining altitude and distance until it was out of effective firing range. The Thunderbolt then leveled off, circled once, and dove back down on Rahl's formation from above. Rahl broke off the engagement. In his post-war memoir, he described the encounter with professional respect. "We knew the Americans had improved their fighters," he wrote, "but this was different. The P-47 could sustain power we could only use in bursts. That changed everything." The difference wasn't just duration, it was operational philosophy. The Luftwaffe treated water injection as an emergency system, a short burst of power to escape danger or press a critical attack. Pilots were instructed to use MW50 sparingly because overuse could damage engines, and replacement engines were increasingly scarce by late 1944. American pilots, by contrast, were trained to use ADI tactically. Republic's pilot manuals for ADI-equipped P-47 seconds included specific guidance on when and how to employ war emergency power. The guidance was surprisingly liberal. Use ADI for initial engagement to close range rapidly, zoom climbs after attack passes, emergency escapes from disadvantageous positions, sustained high-speed pursuits, and climbing to intercept high-altitude contacts. The only restrictions were: don't exceed 5 minutes of continuous use without allowing the engine to cool for at least 2 minutes, monitor cylinder head temperature gauges, and ensure sufficient fluid remains for return flight if operating deep in enemy territory. That last point was important. 15 gallons of water-methanol mixture provided approximately 12 to 15 minutes of war emergency power operation, depending on engine settings and altitude. Pilots learned to budget their ADI usage across a mission, save some for the initial engagement over the target area, save some for the return flight in case of pursuit, use what's left opportunistically when tactical situations demanded maximum performance. The maintenance burden was surprisingly light. Ground crews learned to service ADI systems quickly. After each mission, they'd check the tank level, refill it from 55-gallon drums of pre-mixed water methanol, and verify the system for leaks. The entire process took about 10 minutes. Compare that to engine maintenance, which could require hours or days of work for cylinder replacements, valve adjustments, or turbocharger repairs. ADI systems rarely malfunctioned. The components were simple: a tank, a pump, some lines, and spray nozzles. There were no complex regulators, no high-temperature turbines, no precision bearings. If something did fail, usually a pump or a clogged nozzle, replacement parts were readily available, and installation took less than an hour. Republic's engineers had deliberately designed the system for field maintainability. Every component was accessible without removing major airframe structures. Pumps mounted on the engine accessory drive with 4 bolts. Nozzles screwed into threaded ports in the intake ducting. Lines used standard AN fittings that any mechanic could work with using basic tools. This maintenance philosophy reflected broader American industrial practice. German aircraft often achieved higher performance through complex, precisely engineered systems that required specialized tools and highly trained technicians. American aircraft accepted slightly lower peak performance in exchange for systems that could be maintained by average mechanics with ordinary tools under field conditions. The P-47's ADI system exemplified this approach. It didn't push the R2800 engine to its absolute theoretical limit. German engineers, given the same engine and unlimited resources, probably could have extracted more power. But Republic's goal wasn't maximum power. It was reliable power that thousands of pilots could use routinely without destroying engines or requiring constant expert maintenance. The tactical impact extended beyond individual dogfights. By late 1944, the mere presence of P-47 seconds with ADI changed Luftwaffe operational planning. German fighter controllers knew that American escorts could sustain high performance throughout an engagement. That meant Luftwaffe fighters couldn't rely on outlasting the Americans in extended combat. The classic German tactic of hitting bomber formations in waves, counting on Allied escorts running low on fuel or becoming exhausted, no longer worked reliably. Thunderbolts could engage multiple waves while maintaining energy and performance. Intelligence assessments from late 1944 show Luftwaffe tactical directives increasingly emphasizing avoidance of P-47 seconds when possible, focusing attacks on bombers only when escorts were absent or distracted. When engagement was unavoidable, directives stressed hit-and-run attacks using altitude advantage, specifically warning against extended turning fights or climbing engagements where the P-47's sustained power advantage would dominate. The ADI system proved equally valuable in ground attack roles, which increasingly became the P-47's primary mission in late 1944 and early 1945. When Allied armies pushed across France and into Germany, Thunderbolts transitioned from high-altitude escort to low-altitude interdiction, attacking trains, trucks, tanks, artillery, and anything else that moved behind German lines. At low altitude, the ADI system's benefits changed but remained significant. Down at 5,000 feet or below, the turbocharger advantage that made the P-47 dominant at 30,000 feet mattered less. Air was thick, all engines breathed well, but ADI still provided critical capabilities. When attacking ground targets, pilots often carried heavy external loads, bombs, rockets, or additional fuel tanks. That weight reduced acceleration and climb performance, making aircraft vulnerable during the most dangerous phase of ground attack, the pull-out after a strafing or bombing run. A P-47 diving on a target at 400 miles per hour, releasing ordnance, then pulling up through intense anti-aircraft fire needed every bit of acceleration and climb rate available. ADI provided that. Pilots attacking heavily defended targets would activate war emergency power before beginning their attack run, ensuring maximum performance during the vulnerable pullout. The extra 500 horsepower could mean the difference between climbing out of flak range or being hit. Lieutenant Colonel Robert Basler, commanding officer of the 325th Fighter Group in Italy, pioneered ADI tactics for ground attack in late 1944. His group flew P-47 seconds against German positions in northern Italy, where mountainous terrain and concentrated anti-aircraft defenses made every mission dangerous. Basler developed a technique he called surge attacks. His pilots would approach targets at medium altitude, 3,000 to 5,000 feet, conserving ADI fluid. Upon spotting targets, they'd activate war emergency power, dive at full throttle, reaching speeds exceeding 450 miles per hour, release ordnance, and pull into maximum performance climbs while still under ADI boost. The technique worked because it compressed the vulnerable time over the target. Instead of gradual dives, attacks, and climbs that gave anti-aircraft gunners ample tracking time, surge attacks put aircraft over targets and back to safe altitude in less than 20 seconds. Basler's group recorded significantly lower loss rates compared to units using conventional attack profiles. By March 1945, surge attack tactics using ADI were standard procedure for 9th Air Force P-47 groups supporting ground forces in Germany. The statistics from late-war operations tell a story of dominance enabled by incremental technical superiority. Between October 1944 and May 1945, P-47 seconds flew over 200,000 sorties in the European theatre of operations. They destroyed or damaged thousands of locomotives, tens of thousands of rail cars and trucks, hundreds of tanks, and maintained air superiority over the battlefield. Loss rates during this period, despite intensive ground attack operations, averaged less than 0.5% per sortie. Some of that success came from overwhelming Allied numerical superiority and the collapsing Luftwaffe, but pilot after-action reports consistently credited ADI with providing the performance margins that turned dangerous situations survivable. When you've just attacked a German column and every weapon that can shoot is firing at you, having an extra 500 horsepower to climb away faster isn't a luxury. It's survival. Captain Walker Mahurin, a P-47 ace with over 20 victories, summarized the ADI system's impact in a letter home written in January 1945. "The water injection system," he wrote, "is the difference between a good fighter and an unbeatable one. It doesn't make mediocre pilots into aces, but it gives every pilot options they didn't have before. You can decide to chase that enemy fighter instead of letting him go. You can pull off that attack run even though you're heavy and low. You can get out of trouble when you make a mistake. The Germans don't have that flexibility anymore, and it shows." The post-war analysis, conducted by the United States Strategic Bombing Survey, examined the effectiveness of various American aircraft systems. The P-47's ADI system received specific attention. Engineers calculated that the system increased overall combat effectiveness by approximately 28% compared to non-ADI-equipped P-47 seconds operating in equivalent conditions. That figure factored in kill ratios, mission success rates, and aircraft loss rates. 28% may not sound revolutionary, but in aerial combat where margins between victory and defeat are measured in fractions of seconds and single-digit performance differentials, it was enormous. The survey also noted that ADI systems achieved this improvement at minimal cost. The system added roughly $120 to each aircraft's production cost, plus approximately $5 per mission in consumable water methanol mixture. Compare that to the cost of losing an aircraft and pilot, estimated at over $50,000 in 1945, and the return on investment was staggering. German attempts to counter the American ADI advantage came too late and achieved too little. By early 1945, the Luftwaffe was beginning to receive improved fighters with enhanced water injection systems. The Focke-Wulf 190D9 with Junkers Jumo 213 engine included an upgraded MW50 system with larger tanks, providing up to 5 minutes of operation, matching American duration. The Messerschmitt Bf 109K4, the final production variant of the venerable 109, featured improved methanol injection with better flow rates and cooling. But production numbers were trivial. The Luftwaffe received approximately 700 Ta-152s and perhaps 1,500 Bf 109K4 seconds by war's end. The 8th and 9th Air Forces alone had over 4,000 ADI-equipped P-47 seconds operational by March 1945, with full replacement pipelines, ensuring losses were immediately made good. Germany's aircraft industry, subjected to years of strategic bombing and now collapsing under the weight of ground invasions from east and west, simply couldn't match American production volume. Even if every German fighter had been equipped with systems equivalent to American ADI, which they weren't, they'd still have been outnumbered 5-1. The final months of the war demonstrated the culmination of the P-47's ADI-enabled dominance. During the Battle of the Bulge in December 1944, when weather cleared and Allied aircraft could finally operate, P-47 seconds devastated German armoured columns. Pilots used ADI-boosted performance to attack heavily defended targets, absorb battle damage, and return safely. During Operation Varsity, the Rhine crossing in March 1945, Thunderbolts provided close air support while maintaining air superiority against negligible Luftwaffe resistance. The few German fighters that appeared were quickly dispatched by P-47 seconds, whose pilots could choose their engagement terms at will, courtesy of war emergency power. By April 1945, the Luftwaffe had ceased to exist as an effective fighting force. The reasons were multifaceted: fuel shortages, pilot losses, destroyed infrastructure, and overwhelming Allied numerical superiority. But among the technical factors that contributed to German air superiority's collapse, the P-47's ADI system deserves recognition. It didn't win the air war alone, but it was part of a systematic American approach to aerial warfare that emphasized reliable, mass-produced technical superiority over individual brilliance or desperate improvisation. After the war ended, ADI systems became standard on most American high-performance piston-engine aircraft. The Navy's F-4U Corsair, P-51 Mustangs in post-war service, and various other fighters retained water methanol injection well into the 1950s. The technology migrated to early jet engines as well. The Pratt & Whitney J-57 turbojet, which powered the F-100 Super Sabre and the Boeing 707, included water injection for takeoff power augmentation. Airlines used it routinely into the 1960s to boost thrust during hot day takeoffs from high-altitude airports. The same principle that gave Francis Gabreski's Thunderbolt 2,500 horsepower over Kassel in 1944 boosted airliners off runways in Denver and Mexico City 20 years later. Modern turbofan engines have largely eliminated the need for water injection through improved compressor and turbine designs, but the fundamental thermodynamic principles remain valid and periodically resurface in specialized applications. Alexander Kartveli, the P-47's chief designer, never claimed credit for inventing water injection. He didn't need to. His genius lay in recognizing which technologies mattered and integrating them into producible aircraft that worked reliably under combat conditions. The ADI system wasn't revolutionary in concept. German, British, and American engineers all understood the physics. What made it successful was Republic Aviation's execution. Simple components, field maintainability, adequate capacity for tactical flexibility, and mass production that put the system in thousands of fighters within months. By the time Francis Gabreski pulled that red lever over Kassel in October 1944, he wasn't using experimental technology. He was using mature, proven equipment that had been designed for exactly this moment, turning tactical disadvantage into overwhelming superiority through the application of 500 extra horsepower delivered reliably when needed most. The final tally speaks for itself. By war's end, P-47 Thunderbolts had flown over 546,000 combat sorties in all theaters. They'd destroyed 3,800 enemy aircraft in aerial combat and thousands more on the ground. They'd demolished over 9,000 locomotives, nearly 80,000 trucks, 6,000 armoured vehicles, and countless other targets. Not all of those aircraft had ADI systems. Not every success depended on water injection, but from mid-1944 onward, when the P-47 evolved from formidable fighter to absolute predator, water injection was part of that transformation. The Luftwaffe never imagined that such a simple system could produce such devastating effects. They understood the chemistry, the thermodynamics, and the engineering. What they failed to appreciate was American industrial capacity, the ability to produce thousands of systems, supply millions of gallons of methanol and water, maintain the equipment under field conditions, and train thousands of pilots to use it effectively. That failure of imagination, like so many others, cost them the sky. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.